Okay, hello everybody. I guess I'll be starting. Today I'll be talking about how to make your builds faster in C++. A little bit about me. So first of all, this talk is going to feel like a lightning talk in 50 minutes. There's a lot of ground to cover. I'm from Bulgaria, some C++, some open source. I made DocTest, which is the fastest C++ testing framework. And I'm really passionate about not wasting any time. So no other personal stories. C++ is known for quite a bit of things, but one of them is long build times. And today we'll be talking about this slide, if you've ever seen this meme. So this presentation, you can find the slides online on this link, and they'll be available later. Actually, that link points to the full presentation. Today I'll be presenting 2/3 of it. And first I'll talk about the what and the why, and after that about the how, like all of these techniques and how to improve your build times. So in reality, some projects take even hours to compile, and sometimes even the minimal rebuilds take like 20 minutes because of the linking step. And all projects start out small, but eventually they grow into a huge beast. And this is a case study of the build times for the Opera browser. So in less than 4 years, they went from 15 minutes to more than 64 minutes of build time, even though they incorporated the precompiled header at some point to slow down that process a bit. So this is a unique problem to C++, and people from other languages, they just don't understand what it means to wait for hours to compile your project. Maybe guys from Rust also know that. So why do we want to reduce build times? First of all, it costs money. Suppose, in this case, some average salary for the US. If you waste around 12% per day waiting for builds, and you have, say, 100 developers in an organization, and actually each developer costs a lot more to the company. He brings more value than what he gets as a salary. That actually goes into the millions into wasted money for the organization. And some organizations are way bigger than 100 developers. And there are also some unquantifiable effects, like when your builds are long, you don't tend to refactor that much, you don't want to experiment, and also each time you put on a build, you do a mental context switch, and that's really hard to quantify what effect it has on your work. So any time spent reducing build times is worthwhile in the long run. How do we build C++? First, there's the preprocessor, which takes a source file and turns it into a translation unit. That means all the includes get crammed in, all the macros are expanded, and conditional compilation is done. After that comes the compiler, which takes the translation unit and turns it into an object file. And that's comprised of parsing, optimization, and code generation. And then comes the linker, which stitches together a bunch of object files and libraries into an executable. And there's a really good explanation on that link. Again, these slides will be available later because they will be full of links, which you have to check out later. Why is C++ so long to compile? Well, first of all, it's backwards compatible mostly with C, which was a killer feature for C++. That meant it could get adopted easily. But it means that it inherited the include approach, which was initially intended only for forward declarations of functions and structures. So nothing too fancy in C land. But in C++, we tend to build huge zero-cost abstractions in header files, and the include approach is totally not adequate. Also, the language itself is really complex. There are multiple phases of translation, and each new standard complicates things further. So yeah, all of our zero-cost abstractions end up in headers. Sometimes even the preprocessor becomes a bottleneck. Sometimes we use bad tools and bad build systems. And sometimes we have messed the dependencies within our project. So let's take a C code base and just compile it with a C++ compiler. We instantly get a 12% performance hit in terms of compile times. If we take a C++ 98 code base and we compile it with C++ 17, we get around 30% compile time hit, just because we turned on the standard, even though the library doesn't have any conditional compilation using new features. And in this case, this is only for the front end of the compiler. That means that after the front end builds the AST and passes it in terms of an intermediate representation to the optimizer isn't affected by the language or by the standard, but the front end is affected quite a bit. This meme again, it's going to be a recurring theme. So why do includes suck? They're textual, they're not symbolic. We cannot cache parsed results. Also, we leak many implementation dependencies outside of header files. And sometimes, usually code gets compiled many times. For example, if we have m headers and n source files, we end up having m times n build cost. And templates, we reinstantiate the same templates over and over again in different translation units. And also, because of templates, more code ends up in headers. And each time we write a function inside of a header file, so that's a template function or an inline explicitly marked as inline function, or a function inside of the class body, that's an inline function. And in this talk, we won't care if the function gets inlined in the end, but that means that those symbols are weak symbols. So the function will be compiled in every translation unit which includes this header. And at the end, the linker will have to remove all of the duplicates except for one. So that's additional work for the linker as well. So if we include any of the standard headers and we just run the preprocessor, what we end up having is usually around half a megabyte or even more than 1 megabyte of source code of C++. That's without comments and without preprocessor directives, just from a single header. And if we include a bunch of standard headers, we usually get with more than 2 megabytes of source code. That's just from a few includes. If we include some boost headers, like for example, just boost geometry ends up in almost 10 megabytes of source code. And that's, in the case of Visual Studio, it's almost 500,000 lines of code. And if we include it and a few others, we can reach almost 20 megabytes of source code. So we have written maybe 100 lines of code. We include one header and we get 500,000 lines of code. And we compile that over and over and over again. Imagine what happens if you have 100 source files, including boost geometry. That means you're compiling 1 gigabyte of C++ code. So here the idea is not to bash boost. The idea is that C++ doesn't provide an adequate way to build zero-cost abstractions. Yeah. So first of all, we shouldn't be paying for what we don't use. So we should make sure that there's no unreachable or dead code or functions which aren't called and stuff like that. So there are a bunch of tools we can use which will detect dead code. And again, all of these slides will be available later. All you have to do is save on the last slide, the link to the slides. And we might also uncover some bugs while we remove dead code. Other easy to fix things, we should be using compiling in debug if that's at all plausible. For example, if you're using too much zero-cost abstractions, you might not be able to build in debug. For example, the ranges proposal doesn't have the best runtime performance if it's built in debug. So you might not have that ability. You should also look for source files which you have in your project but aren't really used. Again, this counts to me as dead code. And it sounds trivial, but many projects actually do this without any good reason. And also, we should compile each source file just once. And we should have an adequate build system, so whenever we need some source file somewhere else, we should be able to factor it out easily into a static library or an object library and just reuse it. And this is so common to actually, when you need just one source file, not to link against what you need to, but to cram the source file in. So we should also be striving for loose coupling, and we shouldn't have the include everything header, because when we include that header and anything changes, then we'll have to rebuild everything. This is common sense. And again, there are a bunch of tools which we can use to detect which headers aren't used, and some of the tools like include what you use, they're based on Clang. It is based on Clang, and it can suggest what to forward declare and what includes to remove. And it's really easy to use and integrate. Okay, so again, some of the basics, declarations and definitions. In this case, we see a header file, foo is declared, but the rest of the functions are defined. Actually, we can move all of these functions outside of the header file, including the template function, but that will be shown in later slides. And if you're concerned about moving the implementation of functions outside of header files and into source files, you should just think about link time optimizations or Unity builds. So for types, the situation is the following. You usually know that you could go away with a simple declaration if you're using a type by reference or by pointer. But one thing which isn't commonly known is that in this case, look at the F1 method. There we use the foo type by value, both in the return type and in the as an argument to the function. but still we can go away with a simple forward declaration of that type, even though it's used by value for the forward declaration. And where we define the actual method, that's where we'll be actually using objects of that type, and then we'll need the definition of the full type. And also, if we call somewhere that method, we'll again need the definition of the full type. But we don't need that definition inside of the header file, even though it's used by value in the declaration. And this is basically what I just said on that last slide. Next, we'll talk about PIMPL, which is the pointer to implementation or a compilation firewall. And the idea is that we have a wrapper type which contains a pointer to the implementation. So suppose we have this widget class. It has a public interface, and in the private parts, we have a forward declaration of a type which is the implementation, and a pointer to the implementation. And this is the actual implementation of the widget class. First, we define the implementation type, and then we implement the public interface of the widget class. In the constructor, we allocate a new implementation. In the destructor, we can actually just default it because we're using a smart pointer. And in the public method foo, we just forward the call to the pointer to the implementation. So the pros of this technique are that it breaks the interface and implementation dependency. So you end up dragging a lot less headers into the main header of the wrapper type, and you include them only where the implementation is actually defined. Also, this idiom helps with preserving the ABI, which stands for Application Binary Interface. So a lot of software ships their SDKs and APIs using the PIMPL idiom because if you're a third-party company which builds plugins for the main software, when the main software gets updated, you might not have to even relink your plugins, and they can just continue to work after the binaries of the main program have changed. And that's what ABI stability is for. But there are some problems with this technique as well. So it requires an allocation, and there's also space overhead for the pointer in the wrapper type. But we can use allocators to at least mitigate the problem with the allocations. There's also an extra indirection of calls, but we can use linked optimizations to do away with that. It's also more code to write, and there are many more details about the technique, for example, const propagation, and you should definitely check out the link at the bottom. Also, standard C++, we can define an abstract base class, and then we can have a few factory functions which return a pointer to the base class, but somewhere where we implement the factory functions, we have different implementations of the base class, and we allocate different instances depending on the factory function. Again, really simple. This is all C++. Again, the bonus is that we break the interface and implementation dependency. It also kind of helps with preserving the ABI, but not really, because if we rearrange the virtual functions, or if we add another virtual function to the base interface, then we actually break the ABI. So the PIMPL idiom is much better for ABI stability. And there are a few problems with this approach as well. It requires an allocation, there's space overhead for the pointer, there are extra indirection of calls for the virtual functions, it's more code to write, and users have to use pointers instead of values. And also, linked optimizations will have a harder time to optimize away the indirections. That's called devirtualization, but it doesn't always work, and it's a hard problem. Next, we'll talk about precompiled headers. And the idea is that if throughout our entire project we have headers which are commonly included, we don't want to compile them for each and separate translation unit over and over and over again. We would like to precompile that once and then reuse it for all the source files. And in this case, this example shows some STL includes, some third-party libraries which are hopefully used throughout the project, because it doesn't make sense to precompile a header file which is used in only one of the source files in the entire project, because then that header will be visible to all of the source files when it ends up in the precompiled header. And actually, people should be careful with precompiled headers, because at some point, once it starts going above 200, 300, 400 megabytes, you might start getting diminishing returns. So this is a good example of a precompiled header, mostly headers which rarely ever change, and some project-specific ones, which are so fundamental to the project and change so rarely that it's okay to precompile them and force them everywhere. And you should be auditing the precompiled header if anything new should be added or removed after the project evolves. And this is, the precompiled headers are regarded as a hack by many people because it feels ugly to them, but actually you don't break C++ rules in any way using precompiled headers. And it's an easy way to get somewhere between 20 to 50, 60% speed ups for your build. And if you're building for hours and you get a way to speed up by 20%, even 20, that's still huge. And if it takes you around 1 hour to implement it in CMake or whatever, it's still worth it. How do we use precompiled headers? Well, there are flags for the compilers, but we don't want to be using compiler flags directly. So there are a bunch of build systems which support them. Like for example, for CMake, there are a few open source projects on GitHub which will automate the precompiled header usage. Next, we'll talk about unity builds. And they're also known as amalgamated or jumbo or a single compilation unit. This is actually the technique which has the most potential to speed up your builds. And the idea is that we make a source file which includes all of the rest of the source files. And then we compile that source file. We could actually split a huge target, for example, with, it's not huge, but let's say we have 100 source files. We don't have to cram everything into a single source file. We could split it in 10 source files, including 10 of the original ones in each. And what are the main benefits? Well, if you have a header which is used in at least 2 of the source files, then it gets parsed only once when those original source files end up in a Unity source file. Also, we invoke the compiler a lot less times. But imagine if we used boost geometry and we had 10 of these source files, and now we end up including that header only once because all the source files are in a single Unity source file. Also, if we instantiate the same template over and over again, for example, vector of int in different translation units, we end up paying the same cost, and then the linker has to remove the same duplicate weak symbols of the template class. But when using Unity builds, we actually are going to instantiate the template for a specific type only once throughout the entire Unity source file, because now that is the new translation unit, and it encompasses all of the rest of the ones. So this technique is highly underrated, and the main reason is not the main reason that it's so beneficial is not because of reduced disk I/O, because nowadays file systems are really good actually at caching, but mainly because of the parsing, that we parse the headers only once, and because we don't instantiate the same templates over and over again. And this technique is used throughout the game industry and also in some huge projects like WebKit. They're experimenting with it because build times are awful. And what are the pros of the technique? You can get up to 10 times faster builds depending on modularity. So again, I'll use boost geometry as an example. If you have 10 megabytes of source code from the header and only 100 lines of code in your source file, that's really the ideal solution when you have heavy headers and small source files, which are not a few thousand lines of code. And when you combine those into a single source file, compilation is much faster. And one other thing, Unity builds are actually link time optimizations. Because now you don't have separate source files which you have to link time optimize with a special switch in the compiler in the release builds, which actually takes a lot more time. Because when we use link time optimizations, usually the build time becomes 2 or 3 times slow. And here we get much faster builds and the cross-translation unit optimizations for free. Also, Unity builds are the best way to actually detect one definition rule violations. For example, say somebody has written a class in some source file, and then somebody copied it over into another source file. And then he changed the implementation of the method over there because he didn't know this class belonged in a header file. Now the linker will see the same int method, and after that, since it's actually the same symbol, it will remove the because it's an inline symbol, because it's defined inside the class, the linker will remove at the end one of these 2 methods, and the program will use only the other one, which is left. And this is not apparent, this is a bug, this is a violation of the one definition rule. And Unity builds are the best and maybe only really reliable tool of catching such ODR violations. And it also enforces code hygiene, like you need include guards in your headers. You will find out where you've missed those. But there are some problems. Like some builds might be slower, for example, minimal rebuilds, because now when you touch a source file, you have to recompile, say, 20 source files together. But actually, minimal rebuilds can even be faster with Unity builds, because if the linker has to stitch not 1,000 object files, but only 50, and there are a lot less of the same template weak symbols which it has to discard, there's a huge amount of work which is just not there for the linker to do. And in my last project, which I worked on to implement Unity builds, where I crammed 20 source files into a single Unity source file, I managed to get twice the fast incremental builds for a source file change. And parallel builds, for example, if you have 100 source files and you compile them in a single Unity source file, then there's nothing to parallelize. So obviously you need to tune the system to your needs, so you could actually use all of your cores. Another problem with Unity builds is that some C++ stops compiling. For example, suddenly there's an ambiguous overload resolution, or some other symbol clashes in any way, or somebody has made anonymous symbols with the identical names in different source files, which now end up in a single source file. But all of these can be cleaned up. Like in the last project, I implemented this in around 1,000 source files. I needed 30 minutes of work to go through all of the compilation errors, and they just worked. But the biggest problem with Unity builds is that you could get a miscompilation, where actually the project compiles successfully, but the wrong overload gets chosen somewhere, and you don't know that. And your only line of defense for that is to have a good test suite to actually test your program. So Unity builds might not be the best solution for a production build, even though they're like free link time optimizations. So you have a faster, more optimized binary. But it's a bit more risky. So maybe they're a good idea only while development. And for a full release build, you might want to use normal link time optimizations. So how do we maintain Unity builds? Because we don't want to have to include our source files in the build system and in a Unity source file and manage all that. For CMake, there's the compile time reducer module. Fast build supports them. Visual Studio has experimental support. And all of these, you can tweak how many source files end up in a Unity source file. And also you can exclude certain source files if they're too problematic or if you want to iterate over them. And there are other build systems which support the use of Unity builds. Next, we'll talk about inlining. Inlining is good for faster code, but it's not good for faster compile times. And sometimes we need to explicitly say that we don't want a symbol to get inlined. For that, we can use the attributes noInline and noInline. This almost always leads to compile time savings, and it might even help with runtime. So consider you have a function, and you have 10 points where you return from that function. That means that there are 10 points where destructors are called. And imagine if those destructors get inlined. So you get the same destructor inlined in 10 different places in your function. And that could easily lead to instruction cache bloat. And that would take more time to compile than to optimize for the optimizer, because the same function is crammed into 10 different places. So sometimes it's really useful to disable inlining even for runtime performance because of instruction cache bloat. And this is really useful, especially for heavily repeated constructs, just like destructors. And for example, in my testing framework, each assert is actually a function call underneath. So if you have a function test case and you have 100 asserts, you wouldn't want those 100 asserts to be 100 times inlining the same function. And it makes sense to just generate 100 function calls. Templates. Suppose we have this template, and we can easily factor out the size and the size method outside of the template into a base class, and now, because they don't depend on the type. And now, when we instantiate the template, we won't be instantiating also the size method for different types, because we don't have to actually. It's not dependent on the type. And this way, the compiler will have to instantiate fewer methods for a specific type each time we use the template. And now that it's outside of a template, it's much easier to actually move that size method outside of the header file in the first place. Again, it might not make sense for small functions like this, but this trivial example shows what I'm trying to say. Then there's also less work for the linker when you actually separate template-independent code outside of templates. Because linkers try to remove duplicate symbols even if they're for different types. For example, the size method of vector of integer and the size method of vector of float, they're actually the same binary representation in memory as generated code for the function. And some linkers try to optimize that away. But if you don't do that for them in the first place, they won't have to optimize for it. Yeah. Extern template. That was added in C++11. And the idea is that if we have some templates and we want to use them somewhere, we could say at the start of the translation unit or anywhere, extern template and for specific types. And that means do not instantiate that template in that specific translation unit for those types. You can just use it. It will be instantiated somewhere else. And at the end, we use identity with a Boolean value. And since we haven't told it to be extern templated, that means it will be instantiated right there. That's no problem. So even if we don't say all the types to be externed, it will still work. But for the types that have been externed, in this case, identity for int and float, we have to make sure that somewhere else in the project, in some source file, we have explicitly instantiated the template with those types. And even though we're not instantiating the template when they're externed, we still have to parse them. So extern template works really nicely with precompiled headers, because then we don't have to reparse the templates over and over again. And for example, some STL implementations use extern template for a basic string of char, because that's basically stud string, and it makes sense. It's such a widely used type, it makes sense to extern template it. Okay, we can even move entire function bodies of templates outside of header files. And suppose here is the implementation of this interface, and both the identity and the calculate method are over there defined. But now, if we want to use them, these templates with given types in our project, we have to make sure that they are explicitly instantiated in the source file where they're implemented. Otherwise, we'll get linker errors. So now the user can just use those templates directly for the specific and exact types that they have already been instantiated. And we don't have to pay the price of the compiler parsing the full template and then instantiating it over and over again in different translation units. So there's this thing called the rule of Shio, which categorizes different operations of using templates. And for example, reusing a template which has already been instantiated is almost free. But if you're starting the Sphinx machinery, it's one of the most costly operations you could do in template metaprogramming. And if you want to know more about this, you should definitely check out the talk by Odin Holmes from 2 years ago. He talks about his student who actually came up with this rule and how they actually figured out the cost. Some more notes about templates. You should be careful with erratic templates and also recursive templates, especially when they're not getting memoized. That means you don't reuse the same instantiations. And recursive template arguments, where the template argument grows and grows and grows, now that's something really exciting. It needs to be avoided. Also, now that we have const exprif, we can use a lot less Sphinx, because we can just branch inside of our function based on types or whatever at compile time. And we don't have to use a bunch of templates to use Sphinx. Some tools for metaprogramming, for templates. MetaShell is an interactive template metaprogramming tool based on Clang. Template is again a Clang-based tool, which you could use to profile time and memory consumption of template instantiation. And you can even have interactive debugging sessions of what is getting instantiated. And again, all of these slides and all of these links will be available later. Some other good talks from CPPCon 2 years ago. There was a case study how they optimized their compile times of thrift-generated code, and they moved from Sphinx to type dispatching. And they also showcased Template, the tool to actually diagnose how the templates are being instantiated, and also the F-time report compiler switch, which I'll mention a bit later. And also, if you want to learn more about templates and how they're instantiated or anything, you should definitely follow Odin Holmes and all of his talks. So if you want to diagnose the compilation, like the different phases, like parsing, optimization, code generation, or even subsets of those phases, for Clang and GCC, there are a bunch of flags, which you could actually see different phases, which aren't really user-friendly. They're more geared towards compiler developers, but they could still be really useful in terms of getting an idea where the problem is. Because once you have a source file which compiles for 3 minutes, a single source file, that's something worth investigating. And even if it's only 30 seconds, you might wonder why. For Visual Studio, there are a bunch of flags again. Again, all of these you'll check out later. They're really useful, and some people report really good results after investigating curious cases. Binary bloat. After we have a full binary which is built, we might want to analyze its symbols which are inside of it. And the best tool by far is Bloaty McBloatface by Google. It works on Unix binaries, and it will tell you which symbols take up how much space of your final binary, and then you might decide how to try to optimize your template use. There are also a bunch of other tools for Windows, and yeah, again, all these links available later. Build systems. There are many build systems, and there are a few meta build systems which generate build files for build systems. But it's a huge topic, so we won't really dive into it. We'll just talk about the speed. So first of all, this is not a build system. If you're just calling your compiler directly, it doesn't count. The idea of build systems is to track dependencies, and so you could have minimal rebuilds, so you rebuild only what has changed, and also to have parallel builds. And they also help you manage scale, like includes, flags, links, and you can reorganize your project much easily if you have a nice build system. And yeah, it's a long topic, and this is my slide of just trying to mention a few things about them. But some of the older build systems are showing their age by now. Like for example, MS Build and Make, they're not the most optimal in terms of parallelization, and we'll mention that right now. The fastest ones are Ninja and Fast Build and Incredibuild for parallelization. There are a few other build systems I haven't tested yet, like Mason and Bazel and Buck, but these ones really work really fast. Make, you could use it to be parallel, but for minimal rebuilds, actually the insufficiencies of Make were the reason Ninja was created in the first place. Because when you're working on Google Chrome and you want to do a minimal rebuild of a single source file, it took like maybe 20-30 seconds of Make just to scan all of the dependencies and to see that only a single source file has to be rebuilt. And for that scale, obviously, Make 30 seconds is not worth paying. That's why Ninja was created. And MS Build, you could also build with it parallelly source files. MS Build is the build system behind Visual Studio. But there are some problems with it, like thread oversubscription. For example, if you're building projects in parallel, and each project is building its source files in parallel, you might easily end up with too much threads of compilation on your machine. And you actually end up with a slower build because of that. So that's a pessimization. There are some ways to use Ninja as the backend instead of MS Build in Visual Studio, but I don't know how that exactly is done. Anyway. And also, modern linked optimization technology, I think in all of the 3 major compilers, is also parallelizable. How do we monitor parallelism in our builds? First of all, this is our first line of defense, the task manager. And each time we see a dip from the 100% usage, that means something is wrong, and we should investigate. And there's a really great article by Bruce Dawson, how to actually analyze parallel builds in your build systems. And again, I'll have to defer to a third-party resource. But another thing to mention is Incredibuild. It's a paid solution, but if you don't want to pay, you could actually use it on a single machine without having any distributed builds. But you could make use of their build monitor. And it's an excellent tool to actually visualize, especially in Visual Studio, what gets built in parallel and where you actually have stalls in the pipeline, and where you could actually optimize your dependencies so you end up having a full CPU utilization in your builds. You could also try to use Google Chrome's tracing flame graph view. And it's like an open format. I think it's JSON based, and different build systems might support some way to dump such a Chrome tracing flame graph, and then you could visualize it in your browser. And it's really nice to see what started when, how much it took, and which things were built in parallel. So, sort of winners, fast build. It has a really nice scheduler in terms of parallelizable builds, and it also supports all of these things out of the box, like Unity builds, precompiled headers, caching, distributed builds. You get the picture. This build system does it all. Ninja, it's maybe the fastest one or one of the fastest ones, but it's really low level. So you usually need a meta build system to generate Ninja files. You could use CMake or GN, which was made especially for generating Ninja. Also Incredibuild, but it's a paid solution. And TUP, which I think is not even specific to C++ in any way. I still haven't investigated these build systems, but it's a huge topic. Next, linking. So we should always prefer dynamic linking to static linking. And again, this is a huge topic, but here we're talking about build times. And the idea is that when we link dynamically, we end up linking and using only the exported interface of the shared library. We don't deal with all the functions. We don't have to relocate code and any of that. And for dynamic linking, we'll need to actually... So the thing is, on Unix, all symbols are visible by default when we build a shared library. And on Windows, it's the opposite. On this time, Windows got the default right. And we could make Unix compilers and the system behave like Windows if we use the fvisibility hidden flag. And that means that nothing is exported by default. And then we would need to be explicit about what gets exported from our shared library. And the benefits are, again, improved build times, but also we might get much faster startup times of the program, and also even the final binary in terms of kilobytes of size on our hard disk will be sometimes up to 20% smaller. And for a lot more details about visibility of symbols, definitely check out the documentation of GCC. And there are also a few other flags and some middle ground, like fvisibility inline is hidden, where you don't have to annotate your interface explicitly, but yeah, if you're curious, research them. For multi-platform symbol visibility marking, you could use the following. So in this case, first we define the symbol export and symbol import symbols with compiler-specific pragmas and not pragmas, but attributes. Then, depending on if DLL exports is defined or not, we either define my API to mean export or import. And after that, we annotate our API in the header with my API, and we just say that we want to export full and also the entire class. And now, when we use this header, when we're building the shared library, all we have to do is define DLL exports for the for the build, and we'll export the symbols we have annotated. And when we want to consume this library and link against that dynamic library, we just don't have to define anything. We just have to include the header and use it. And this is how easy it is to be explicit about what to export from your dynamic libraries. Linkers, again, they're a big topic, but what I could say, on Unix, you should be using the Go linker instead of the default one. It could also link with multiple threads. You could also make use of LLD, which is part of the LLVM project. It's also multi-threaded by default. It might be even faster than Gold. And there are a few other tricks which you can employ, like splitting the debug information outside of the final binaries on Unix. And yeah, link time optimizations. Clang has this thing called thin LTO, which is scalable and incremental link time optimizer. So link time optimization technology is getting much more tolerable and more stable and doesn't consume that much memory, and it's even incremental in this case. GCC are also doing a lot of improvements, and Visual Studio, here I'm not only mentioning LTO, but also their linker throughput in general. They also, a few years ago, they introduced a smaller, more compact and more optimal PDB format, which is the debug symbol format for Visual Studio binaries. you need to use debug fastlink, and for any new project, that flag is on by default. And again, all of these flags, you should definitely check them out later. Compiler caches, what are they? The idea is when you submit a source file, a pre-processed source file, that means a translation unit after the preprocessor has run, when you submit that to the compiler and with a specific set of options for its compilation, if you submit that to a compiler cache, it will check if there is an already built object file for that exact input, and if there is, it will just return you that object file. Otherwise, it will call the compiler, it will compile the code, then cache the object file and return that to you. And here's an example. The first time we build a project when the cache is called, so there are no object files from previous builds, the build is just like a normal full build. It actually might be like 5% slower because the compiler cache has to cache the object files. But later, in a consecutive full rebuild, so if we issue a full build again, we'll actually reuse all of the object files. And compiler caches, they're useful not for minimal rebuilds. So if you touch a header file and your build system rebuilds only 5 source files because of that header file, obviously you won't benefit from a compiler cache because you end up with 5 different translation units. They'll be different from previously what was used. So yeah, compiler caches aren't useful for minimal rebuilds, but are really useful for continuous integration. When you push and there's a full build going on, but actually only a tiny amount of code has changed, you would want, in an ideal world, to reuse the majority of the object files. And for Unix and Windows, there are different tools. Ccache is the most famous one. FastBuild, the build system supports caching. And there are also cloud storage caching solutions, also for Visual Studio. And there's also this thing called zapcc. It's a Clang fork of the compiler, which doesn't function like the compiler caches I just talked about. It's something else. The idea there is that the compiler is a daemon which stays alive in memory, and when you compile a source file and then you start compiling a separate source file and you have the same templates which you instantiate over there, it will reuse the instantiated templates from the previous source file if all of the context of the instantiation matches. And it was recently open sourced, and some projects can compile even for their first initial build, because that's the goal of zapcc. It's not for consecutive full builds like Ccache. It's only for even for the first build you issue. You could get around 2 to 5 times faster builds on template heavy code. But the future of that project is not really certain, and it was really a good case study. So maybe it might get incorporated upstream into Clang someday. I already mentioned this about caches. You could easily integrate a compiler cache through CMake, and actually a compiler cache is a compiler wrapper. So for example, with Ccache, when you want to call GCC, you just call Ccache GCC. So GCC is a parameter to Ccache on the command line. Distributed builds. The idea is for us to leverage the machines or our network to do our bidding. Like, we're a client and we want to build our entire project, which is huge. So we tell the scheduler of the distributed build setup that we would like to utilize all of the available machines to help us out with different source files and object files. So we end up sending the source code, or maybe depending on the build system and the distributed build system, maybe you don't have to even send the source code, I don't know. But then what you get back is the object files for that compilation. And I think almost always in all solutions you do the linking locally, but I'm not sure about that. But the idea is that the compilation is done and offloaded to a bunch of other machines. You could configure how many cores to dedicate from each machine, or if somebody is working on the machine to not dedicate any core from it. It's really, you could configure it in any way. And just like compiler caches, distributed builds, usually like distcc, which is the most famous such tool, is like a compiler wrapper as well. So you can just prepend it to your compilation command. And actually, you could combine a compiler wrapper such as distcc with Ccache and you could end up having distributed builds and caching at the same time. And again, DCC and ice cream are the most famous tools for distributed builds. Fast build supports them out of the box, and yeah. Hardware. How do we solve problems? We throw money at it. Yep, this is what I will be talking about. Basically, you need more cores, and you should make sure you have enough RAM because you'll be doing parallel builds and lots of linking. If you have a lot of RAM, you could use a RAM disk, which is basically file system drive in your RAM. So if you have 100 gigabytes of RAM, you could use that. And what makes most sense to put in a RAM disk is the temp directory and also the output from the build, and sometimes even the compiler itself. So it gets started faster each time the process is started. And there's a great talk from 5 years ago from CPPCon by Matt. He talks a lot more about hardware, about profile guided optimized builds for the compiler, and many other things. But what if your fundament is bad, like the architecture? Physical design is really important, and many people neglect it. And whenever we start a small project, it's always like a demo or a prototype, and then it ends up being the real thing, and we never clean things up. And it's actually really important to think from the start, or at least whenever it's possible, about the separate components and the modularity of the code. And that will allow us to have faster builds and to be able to reason about the code, what interacts with what, if we want to cut dependency, how to actually go about it. So thinking about physical design is really important. And there are many resources on the topic. And one person who stands out is John Lakos, who has an old book, but it's still quite relevant, and a lot of talks about building modular code and in large scale. So you should definitely check out his talks. And some companies go as far as disallowing the inclusion of header files in other header files. So when you include a header file, that's it. It cannot include other header files. And they're actually pretty good developers. They've shipped a huge game engine which got sold to Autodesk, so they know what they're doing, but they hate the compilation model of C++ so much that they have gone to this extreme length to not allow header files to include header files. I'm not saying that that's the right solution, but that just goes on to say how important physical design is to some people. Dependency analysis of the physical design. We could make CMake output a GraphViz file, which we could later feed to GraphViz to generate us a visualization of the graph of the dependencies. Also, most build systems support also outputting such a graph. And most of the tools from one of the earlier slides for finding unnecessary includes, most of them also support outputting a GraphViz file. This is one such example. This is boost variant and what it depends on. And looking at it like this, it's much easier to reason why something depends on what, so you don't get surprised. And it's much easier to reason how to go about it if you want to make it more separate. But maybe you're curious about modules and what they'll do. We had a really, really good and thorough talk just before mine over here. But I'll try to contribute a little bit. The first proposal was 15 years ago. Yeah, I'll let that sit. The first work on the first implementation was started in 2011. In C++ 14, they continued the push to standardization. It didn't end up in C++ 17, but it will, I think it's already sure that it will enter C++ 20. These are not the latest papers because there's a new batch of papers from 2019, but you could find those. And what's the motivation? Compile times is one of them. Also, we really hate preprocessor includes because we leak symbols and implementation details. We have clashes of names sometimes. Tooling is hard. We end up with 10 megabytes of source code. And we have to be careful about the include order because that matters as well. And also, we want to keep things more dry. We don't want to have forward declarations. We don't want to have that separation of header files and source files. It's non-existent in our languages. So here's a quick example. In Visual Studio 2017, we export a module, we export a function. Again, there are much better examples in the previous talk in the same room. Then we consume that module, we import it, and we just use the getStrings function, and it just works. We compile it like this, because there's no build system support yet. We have to use the compiler on the command line directly with a bunch of flags, and it's not really pleasant. How do they work? A really not very thorough description. We have binary module interface files, which whenever we include a module, we consume such a binary file. And these files are actually produced when we compile the module interface unit for that specific module. So there's an interesting problem of how actually to generate those BMI files and how to do the whole compilation. And build systems are currently trying to figure that out. And unlike precompiled headers, at least, so binary module interface files, they usually contain something like the AST of the parsed and compiled module. And they're something like precompiled headers. But unlike precompiled headers, a separate module or a separate translation unit now can use a bunch of such modules. But with precompiled headers, a single source file could use only a single precompiled header. So modules are composable, unlike precompiled headers. And also, we're explicit about what to annotate and define as visible outside of the module. Some techniques for build times are obsolete by modules, like the PIMPL idiom, because now you'll be using the PIMPL idiom only for ABI stability if you need that. Forward declarations will be mostly gone, precompiled headers will be mostly useless, and Unity builds, depending on what you want. You might still want a Unity build. I wouldn't, but maybe if you want link time optimizations, maybe you could use Unity build for that. In the current state, big companies want modules. There are implementations in the 3 major compilers. They're coming in C++20. And when they're fully standardized and implemented, you shouldn't expect astronomical gains, especially as we saw in the last talk, because the production of the BMI files is actually, and the discoverability of modules is an unexpected problem. And currently only build 2 as a build system supports modules. And also, even if all of our toolchains supported modules in a standard and uniform way, we would still have to update to those toolchains, and then we would have to change our source code a bit, and then we'll have to rely on our third parties to actually make use of modules. And I guess you've heard, if it ain't broke, don't fix it. So my take is that we'll be dealing with legacy code for quite a long time, and the PIMPL idiom is not yet dead. The next steps, you should consider runtime compilation, so you don't have to recompile your entire project and restart it, but hot swap code at runtime. Make your source checkouts faster, use my testing framework for your tests, of course. And you didn't say that last part. And that's it. Any questions will have to be taken later.